Before I start with the lecture, let me mention that I had planned originally to cover also double categories and then some aspects or some role of them for string nets, which I will talk about today, but there was no time to do it. I will not do that. And nevertheless, I have too much material for today, so I cannot cover all of that. But I want to have a decent end to the lecture. So depending on how things are going, I might be a bit over time at the end. So as I said, today I talk about string nets. And I start with the construction and then explain relevance of the construction for conformal field theory, and then in the last part talk about generalization, which uses bi-categories as an input. But we start first with recalling the notion of modular functor. In the first place, this was a symmetric monoidal functor, which I had denoted by DL, where this reminds of blocks, conformal blocks, which goes to the cobordism category, oriented manifold with dimensions and open closed, meaning that they might have boundaries to vector spaces. But then I already explained that one could generalize this to two functor or pseudo functor symmetric monoidal from this category regarded as a bi-category, which I described, to the bi-category of pro-functors. Okay, so which is finite linear, k-linear categories as objects, and then as morphisms, not functors, but pro-functors. And today I will give you a particular construction of such a functor. And we'll start with basics of the construction. This has algebraic and geometric aspects. And we start with the following. First, the algebraic input. This is pivotal or maybe even spherical, but for essentially everything I do pivotal is enough. Fusion category, which I denote by C. And I should mention that one motivation to what I will talk about is actually to go beyond semi-simple situations. But everything I'm doing now is completely okay for the semi-simple case. But it's also clear from the construction that large parts will generalize to non-semi-simple situations. It's less clear whether whether one has a complete picture in that case, or if one has it, whether it really gives some new insights. Then there is a geometric input, which partly are entities we have already talked about, namely objects of this cobordism category. And I will just refer to them as surfaces. They are always oriented, compact, and smooth, but I will just say surfaces. But that's not. Also, these surfaces I will typically denote by sigma. But then, in addition, graphs embedded in sigma. And also for the graphs, one has to give a precise definition. In particular, they will be oriented. but I will largely suppress orientations. Partly in some pictures I will draw them, and I also will not give a precise definition of graph. When I talk about graph, it will always be a graph embedded in a surface. So really, I would have to specify also the embedding. So if I want to do this, then I would call it phi, say. There is an abstract graph, and embed as a one-dimensional stratified submanifold of sigma. And what is important, we require that the image of phi consists when we look at a part which lands on the boundary of sigma, then this is a finite number of distinct points. So the objects here are I said surfaces. The objects are one manifolds. I refer to the morphism for surfaces. Objects, I should say, and morphisms. Strangely enough, I didn't say this here precisely. And so what does this look like? The boundary will have several components that will be either circles or intervals oriented, but I said I suppress that. And so if I have now my graph gamma, then the intersection with any such boundary component will be finitely many points. And in addition, I don't write this up. In the case of intervals, I also impose that none of these points is an endpoint of the interval. Is there a reason why? We will see that shortly. I could explain it now, but it would not say so much. It mainly, as long as we do the construction itself, it's only for technical reasons, but in the application to a conformal field theory, it will be important. When I say in the rest of the lecture graph, I always mean a finite oriented graph embedded in this way in a surface. And then there are further algebraic C coloring of the graph. This is just what you would expect. Namely, to each edge of the graph, you assign an object in C, and to each vertex, if you have objects X and Y here, accounting for orientations, then this would be a morphism from X to Y or the other way around. And here we have actually to be a bit careful about orientations. If I change orientation, and originally I had the label X, then if I change it, this will naturally be the dual label. But if I do this twice, then I get to X double dual, and that's why we require pivotal. So, and we also know we can trivialize pivotality, and that we do implicitly also. And now, more precisely, we have a vertex V, a vertex V here, and we associate to this phi of V, which is a morphism in, and now I write something and then I have to explain a little bit from the tensor unit of C to, sorry, to, maybe yeah, this is okay. I have here, you should have complained because it's not from X to Y. This is say from X1, X2 to Y tensor. Okay. And there are three lines altogether. And so in this case, I draw, forgetting about orientations, I write this as xi1, which would be x1, or just x1, tensor x2, and so on. Just final numbers of xl. So if I do that, I think of all the lines as incoming, as outgoing, and also on the circle. No, first on the interval, I have used the orientation to have a linear order. On the circle, I only have a cyclic order, and I have implicitly chosen some parametrization where I split it up somewhere, but the result should not depend on that, and therefore this is actually to be thought of as in terms of the limit of the corresponding graph. And then this is possible is right. This gives something well defined, which matches the situation is as explained in 686 for pivotal categories. We have a graphical calculus on this, not only on rectangles. So concretely, if we have a situation like that, we can use the dualities to get the totality to replace it by this, changing the order, keeping the cyclic order, and then instead we think of this as number one. Now we have colorings. The next step is isomorphism of colorings. So let's write the coloring as some colors for the edges, set of edges, which I denote by capital E of the graph, and some coloring by morphism of set V of vertices of the graph. And then we say that the coloring of even form is equivalent to the coloring prime if and only if we define this as the collection of isomorphisms of the relevant objects. So I call them FE for every E in E, the set of edges. However, actually, we do not take E, we take E hat, and this is defined to be E combined with, if we take any edge E, we denote by E1, the same edge with opposite orientation. And so effectively what we're thinking here of are half edges. And we require, of course, that if we have an edge consisting of two half edges, if we have the color X here, then the color the X2. other side. And so these isomorphisms FE go from the color for the HE to the color or the same edge with the new prescription. And such that FE dual composed with FE bar. This, by definition, you can see is the identity on the color given to the HE, to the HE bar. That this is a morphism in the this is an endomorphism of this type, and we require that it's the identity. So it's just compatible in the natural way, and then also if we look at the vertices, then for a given vertex V, we get the new color, but the two colors are related by applying FE to each of the incoming lines. So V in, let me call it this VE, the edge is attached to vertex E after the So these are colorings, and now given the coloring, further concept is we call the boundary value. Sometimes I will say boundary datum. This will mean the same thing. This is assigned to a coloring. This is a map from let's call it call with a boundary symbol from VD to C, where this is the set of all vertices such that they lie on the boundary, and as I had prescribed before, all of them will be univalent. And how is this? What does this look like? Well, again, accounting for orientations, either once they says that I the edge E at V, which I denote by this, it's incident when I give it the color of the vertex, the color of the edge, and otherwise I take the dual no. This should be outgoing, and this is incoming. That's the convention. So here we get a boundary value for a given graph embedded in the surface, which gives us then some information on the boundary of the surface. But we can also define a boundary value for the surface sigma. which is just then something which, in the case of a graph, you get in this way. So this is a collection, and I denote it by B, of finitely many mutually distinct points on the sigma together with a corresponding map. Which I denote by B0. Maybe I call this a little b here, in order not to get into conflict later on. So I just give, I just select some isolated points on the boundary and label them by object of C. And then we do something bold. First of all, we look at a set which I denote by G, capital G, of sigma and B0, which is the set of all C-colored graphs. Let's call them gamma, such that embedded in sigma, of course, such that the color for gamma, maybe I put a gamma here, associated in this way, is given by the prescribed boundary value. And once we have this, we define a vector space, which is the vector space really generated by this set. And this is denoted by K, the underlying field, G of sigma B0. And this is the K vector space. Really generated by this set. And this is the huge space. If I just take a graph and modify it a little bit locally, then it's a new graph, a new embedding. Also, if I use some identities involving objects and morphisms of C to get something new, I get another graph. So this is completely unmanageable, but this is not the space we are interested in.
It's not how there's a more sense of color.
Yes.
From the
They should be, they should, did I write this up? We need isomorphisms between the boundary values should be kept the same after isomorphism. I haven't written that after this as an equation, but that is it.
by up to isomorphism.
We have, let me see, we have it's implicit. We have these isomorphisms from the coloring of E to the coloring to another coloring of E, and we have this requirement about No, it's you see for one valid vertex, if we have we just said we have this isomorphism F here, and we have to compose it with the morphism that we have here. So it's a special case. It's just a special case of the general formula that I have.
Right. Okay. So we're allowing the isomorphism to change the value.
Yes, it will change the boundary value, but by these isomorphisms F, which in addition have further properties. Before I continue, let me give you an example. Let's take sigma to be this B. We have this. We have some isolated points on it, which are labeled by object x1, x2, and so on. And then T0, which was the set, x1, x2, and so on. Which we can also think of an ordered set when we do this extra choice. And now, you see, if we think of this as morphism, we assume that this would be resulting from some morphism here on the disk with these objects corresponding to in or outcoming lines to the disk, then by the graphical calculus for this. This will correspond to morphism, some morphism in this morphism space 1 in C, x1 in the x2 and so on. And again, only the cyclic order is relevant. And by this, one gets canonically a subjection from this big space. This one boundary value. Let's call this kind of evaluation of this. This vector space. Or put differently, I can describe this vector space as this large space divided by the kernel block. And this works. This I can do for any disk. And now the idea is to extend this to arbitrary surfaces. And take some surface sigma. And we consider an embedded D such that it doesn't touch the boundary. So the sigma with theorem of reflection. And then we define what's called a null graph. Actually, we now use the term graph not only for extra graphs, but also for linear combinations of graphs, just in order not to always have to say linear combinations. And this is by definition an element in this a big space. So some Ci gamma I with the following restrictions. First of all, we define this with respect to this B, and we say that no vertex of any of the gamma i's lies on the boundary of the disk. And every edge of gamma of any of the gamma I intersects EV transversally. In other words, if we have our graphs, then we can use this like that, but not like that, for example. Or also not, if the graph happens, there could be a half circle passing somewhere, it will not lie on the boundary. And further, importantly, if all the gamma i's look the same except on the disk, and if we restrict them to sigma minus the disk, then they are all the same. And finally, if we now apply this evaluation in D, so that you get sum over I, Ci, and then gamma I intersect with D. This will be a graph on D, and for that we can use what we did before. So we can apply this map here, such that this will be 0. And then we define the null space. And N of sigma and B0 to be the subspace of this big space spanned by all null graphs with respect to all, meaning all satisfying these requirements, disks embedded into sigma. And then the final definition now, where we use the word a string net, we call the string net space for sigma and B0 to be the quotient. Yes, I write Sn for string net, C of sigma and B0, S K B of sigma and B0 divided by N of sigma and B0. And I put a 0 here. I will explain this later on. And notice this is a huge space. This is also still a huge space. It will turn out that the quotient is actually finite dimensional, but it's not so easy to see this directly. It's quite a bit later. Some remarks. And first of all, I said that I use a graph also for linear combination of graphs, but I will also use it for string nets. So often use graph and also the notation gamma for really the class in the stringed space. And the terminology is stringnet. Sometimes we, in order to indicate the zero here, which I have not yet explained, we call this also bare stringnet space, but it's not always used. Yeah. So that is the rest of the remarks. No, there is something more. By construction, the string calculus for C on disks, because C is pivotal, is valid locally on the surface, meaning in particular that we have that we while this identification we always deal just with morphism spaces, combinations of morphism spaces, and this means that the dimension is finite. Then also SNC 0 is linear. The color of each vertex. And it is additive with respect to the equivalent sums of colors at the edges. And also as the topic graph represent the same stringnet. Simply because the difference is easily seen to be a null graph. And in the same way, graphs with isomorphic elements. So I use one of those isomorphisms of colorings. So this is all very easy. More important, diffeomorphisms of the surface act naturally on graphs. First, they deform the graphs with some new graph, and this together with this fact here that isomorphic graphs give the same string element in the string set, we get an action of the mapping class group of sigma on the stringnet space. We'll do more. Stringnets can be concatenated via sewing. And I don't write anything about that in detail except for some notation. You just like in sew surfaces, when you have graphs with matching boundary values, you just take them the graphs together. What you then get is for each point on the boundary that was part of the boundary datum, you get a new two-valent vertex on the graph, and that you just color by identity, respectively, depending on and then you can actually omit it, and I write this as I start from a graph gamma, and if I have a circle or interval along which I concatenate the graphs, then I write this in this form. And gamma could be consisting of two disconnected pieces which I glue together, or it could be then the genus will not change, but it could also be that I have a single connected component with a boundary B, and there's a natural notion of dual boundary datum, and if I bring them together, then the genus will increase by 1. And this I can do for graphs in the first place, but clearly this lists the string nets. So if I take a given string net, take a representative graph with it prescription, and then take the string net, the result will not depend on the representative graph I have chosen. Now, as it turns out, what we have been doing so far is nice, but not nice enough. And this brings me to the question of idempotent completion. So we have a finite dimensional vector space with an action of the mapping class group and behaving nicely under sewing, but in the application to conformal field theory that we have in mind, actually the boundary values on an interval will correspond to some boundary field or generalized boundary field, and those on circles will correspond to generalized effect fields. And those should be objects in C, respectively, in the Greenfield center of C. And at the moment, we don't have any categories yet. And also, there's a natural way to associate categories to boundary data, but this will not be directly enough. And so this is the first point. We define a category. We promote the boundary values to a category. Which I denote by CIL, which stands for cylinder, still with this extra index. 0 is the category of boundary values with colorings in C on a one manifold S, where the objects are boundary values B0 on S, and the morphisms are given by string nets on the cylinder. So home in the cylinder in this category from B0 to B prime 0 is the vector space and B0 on surface S times the interval, so the cylinder over S with boundary values, boundary value given by B0 together with B prime 0, and for B0 we have to take into account opposite orientation. And then also composition is concatenation in this sense. Now we have to take the break. Let me already announce that this is nicer. Now we have a category, but in general, this cannot be the right category. And this is because it turns out these categories are not idempotent complete. Additional categories that we get are typically not idempotent complete, and therefore also not, in particular not abelian. But that's not what we want. And there is simply no reason why they should be. But we can easily make them idempotent complete by just completion. And then it turns out, but I will not try to prove that they are actually abelian and that they work in the way that we want to use them. So we give the following definition, and this is now called the cylinder category, associated to boundary data, to one manifold F. ES. That's a European envelope idempotent completion of the category that we had before. And that means that objects are pairs consisting of a boundary value and an endomorphism in the cylinder category, which is idempotent. So remember what the morphisms are. So we have our boundary value point with corresponding colors, and then we look at the cylinder over it, and phi will then just be some string net on the cylinder, or represent the graph or string net on the cylinder with this property. And instead of thinking of pairs, we can just think of this idempotent, because when we know in which space it is, the boundary value is implicit. And then one can show that if you look at cylinder category, well, it follows easily. If you have disjoint union, one manifold which can be written as a disjoint union, then this just gives the direct product of the corresponding cylinder categories. And furthermore, we can replace them by the delinear product. All our categories are in particular finite, so the delinear product is defined. And in the case that we actually consider Nemi simple, this is automatic. If we work more generally in the context of finite tensor categories, then actually for this, what is needed is that all the functors that will be relevant are all left exact or all right exact. Because if I compose, if I have both of them, then the cylinder, the linear product is not well defined. And that means, in particular, that we can consider just S equals circle or S equals the interval, and then everything else will follow. And now for the circle, things are very easy. One can show that there's a canonical equivalence between the cylinder category, but even the in principle, idempotent complete cylinder category for the interval MC. But since C is already idempotent complete, we have such an equivalence, then actually this means that already certain zero is idempotent complete. So there is not much to say. In the case of the circle, things are more complicated. And as an input, one needs the following proposition due to Bakanov-Kirillov. Try to make this short. We define L of X for X in C to be the direct sum over all simple labels lambda, while lambda tensor X tensor Y lambda dual. And then one can show that naturally L of X for every X in C is an object of the Greenfeld center, meaning there is a natural half grading on it. And in fact, you could really think of this here as a coend X, Y in C, Y Y dual, and then the half grading is easily expressed in terms of the natural transformation of the coend. Also, the coend actually has a natural structure of algebra in the category of endofunctors that means the monad, and this monad plays an important role in the for the central monad. Also, this defines in fact functor L from C to the center of C. Not only for objects, but we can do this for morphism. It gives a functor. And then this functor is a two-sided join of the natural functor we have in the other direction, in the potential functor. Now in our application, to strip in our context of string maps, we can use this result. By precomposing this with prescriptions that we have had, the canonical functor call it capital Phi 0 from the cylinder category for the circle to the Greenfeld center. Because on the circle, if you just take this with some choice a starting point, a tensor product of the objects, we get an object in C, and then this way we get an object in Z of C. And this is on objects and on morphisms. This is given as follows. if I have a morphism, let's for simplicity just take one point and denote it by x, which need not be simple, could be tensor product, and then another one where I have a different x prime, then this is given by string nets of the form I have x here and x prime here, and then representative graph of this form with some morphism here, where this the ladies here correspond to the y lambda over there, and we have to sum over them, and then we can check, and this is a important result, which I will not prove. The proof is actually rather lengthy. That see, could I? There is a zero missing here. Otherwise, I now, but this clearly extends to a functor where we have the full cylinder category, which I then call phi. And now there is the following proposition by Kirillov that phi is going to here is an equivalence. And let me just not even indicate anything about the proof, but just give an example in this situation where we have a circle written one object x. So this would be our B0 in the non-idempotent completed, and then in this case we have an object in the full cylinder category, consists of B0 and an idempotent, called B now, because of some application that I will, however, not have time to we have x, and then we have just a cylinder here, but then we have an additional part of our graph, where this here is the half grading, and here we have what is called a Kirby color, and fortunately this is defined as direct sum over all lambdas, d lambda divided by d squared, that is the dimension of the category, times the simple object y lambda. This is of course not or not an object, strictly speaking, but what is meant is that when we deal with morphisms, we have corresponding sums. You see, somehow, no, I left out 18, no, it exists, so I continue with 990, and now we would extend this to stringness on sigma, so we know what to do with one manifolds, and we define now the following for a certain sigma with boundary value B0 on B sigma and an idempotent on the beginning P in the in the cylinder category for the boundary from say x to y. We set P star, P lower star, to be the morphism of Sn0 stringness for an endomorphism of this, which is the linear endomorphism of the space that maps graph stringnet, but say representative graph for this gamma. Let me write it here. To what I get by gamma concatenated with P close to the boundary. So, for example, in the case of which is no longer there for a circle, where we here we would just at each boundary component, boundary circle where we have some x, we would introduce an additional copy color here, and then we do for all the components of the boundary. And when one shows this star is an idempotent. And this is simply because what we have here is an idempotent, and that follows from simple calculation, which is the reason why the curving color was introduced in the first place. And now we define the stringnet space for the idempotent completed a situation. So this is an Sn without zero for sigma and B, where B is is B0 together with P. The image in the uncompleted string net space of this projected star. Now we can define or come to the point where we have a deal with a modular functor proposition. The assignments of the cylinder category for S for one manifolds and surfaces together with a boundary value to this assigned a string net space. Extend to a modular functor. Well, let's first check that this can make sense. This is a category with all the satisfying all the requirements for being an object in profunctors. And here we have a vector space, but we can think of this as the obtained from a profunctor. So therefore we say here extend. And let me first say that in the situation that we have only closed surfaces, this was proven by Kirillov, and then the extension to the open case is not particularly complicated. And a few further results. Assume first that we are in the closed case, so the boundary is disjoint union of, say, L circles, and also assume that sigma is connected in the first place. Then there is a non-canonical equivalence of the cylinder category for S for the boundary of sigma. So here true. The L-fold, the linear tensor product of the Greenfeld center of C. This is non-canonical, but actually it's easy. It's anyhow preferable to work directly with the cylinder category. And we know it's isomorphic to that, but we don't have to specify the isomorphism for most arguments. And then we get the proposition that in this situation, in the case that this, if we apply this phi, the sigma to V, we get the linear product over object xi in this category. And then the general case will be direct sums of such. Then there is an isomorphism . between the string net space for sigma and boundary facing to the morphism space in the Greenfield center from 1 to, let me write this first, by a tensor, the sigma of B tensored with L, let's see, to the tensor power G, where G is the genus of sigma. L is the Lukashenko coend, which I described some time ago, which is just L of 1 in the notation before for the Greenfield center. And that was the notation before was for C itself. So therefore, I have put this label here, and this here is just when I have this the linear product here, and I just take the tensor product of all these xi's. And in addition, this intertwines the action of the mapping class group on two sides. And what is that action? Well, on the left side, I have described it. Well, it's just using how diffeomorphisms act on graphs. This is geometric and it's very simple. On this side, there is an action of the mapping class group by actions on these tensor powers of L, by explicitly given morphisms, which, however, are complicated. So there, one takes a certain presentation of the mapping class group, and then for each generator, define separately a certain automorphism. In the case of the torus, for example, for the S and T transformation, but at higher genus, it becomes pretty involved. So this is a nice way to get to describe the mapping class group actions in terms of stringlets, which on one side is simpler, on the other side also you directly get this relation here, this connection between the two. And
so is there a way to kind of relate the string net space to?
The answer is yes, but I cannot tell now. I would have to look it up. Actually, there is a paper by someone else where the scheme theoretic descriptions worked out. But I even forgot the name now. If you're interested, send me a mail and then I figure it out. And it's clear that if sigma is not connected, let's say sigma prime is connected, this triangulation with sigma double prime, then the string space is just the tensor product of S and X prime and B prime, then also the analogous expressions. B prime is B respective to sigma prime and analogously for what will be double prime. And in particular, it follows that for any sigma, including non-connected ones, we have an exact functor from the cylinder categories on for the boundary value the vector space. Now, the next thing I will try to keep short. In the application to CFE, the sigmas, the surface that we have are what I have called sigma S, some lectures before, where S is a worldsheet. And remember that for worldsheets, the boundary comes with a parametrization. A part of the boundary, maybe those not corresponding to physical boundaries. So here I have parametrized boundaries. And this doesn't appear in what we have been doing so far, but actually we can extend and then one has a corresponding stringnet space obtained from the previous one composed with pseudo boundary parametrization, but typically one suppresses this in the notation anyhow, so I will not go into further detail. If one puts these information together, then one can show the following. I take a sigma with boundary parametrization, and I don't write this in any detail, but remember that this in particular means that we have two maps phi minus and phi plus, where the image of these are regarded as incoming respect to the outgoing parts of the boundary. So that means that we can in particular look at the situation that phi minus goes from alpha disjoint union with beta to the sigma, and phi plus from beta, same beta disjoint union at some alpha prime. And in this case, we can give a surface, we can glue to get a surface, glue along beta to get a surface that I have denoted in this way, including boundary parameterization, which I suppress. And then there is a gluing transformation. Of an appropriate type that exhibits the string net space for the glued surface. And now Let me write this. I first write it. No, that's too much. Two variables here which correspond to the boundary values on alpha and alpha prime, which I don't want to specify, so everything is functorial in this, and this as then as a co-n. So S in C of the fluid surface can be written as the co-n over all B into cylinder category for beta. And then we take, and now we have to call this B prime, and here B bar prime. Yes, where here, as before, this corresponds to alpha and alpha prime. This is for beta, and this will be for the second copy of beta, where we take the dual boundary value. And now this actually applies both to the case that sigma is connected and I have self-flowing, but also when it's disconnected. And to be precise, the co-end here has to be, and that's the reason why we think of this as functors, has to be taken in the general case where we are not semi-simple in the category of left exact functor. In the semi-simple case, there's nothing to talk about. And in particular, also when sigma is disconnected, then the space here can be naturally written as a tensor product. And by iteration, by starting from the simple surfaces with at most 3 boundary components, you can stack things together such a way that you always get these spaces that I have described before with this Lukashenko co-end. Lukashenko co-end comes from the self-fluing. I wanted to say few things about applications in conformal theory, and I see that I have to be very short about that. So give me, I will. Some main steps. And so we consider a worksheet S in the corresponding surface sigma S, which I have described before. Then if we have a string net here, this corresponds to a network of here I have a network of defects in general, and remember that corresponds to bimodules with respect to the algebrans that label the 2 patches, the 2-dimensional cells, and if we apply the forget functor from bimodules to underlying objects, then this gives me actually a graph, which I then call a gamma S of the type before. So both for the vertex for the edges where I have bimodules, and for the vertices where I have bimodule morphisms. These are then I just consider as morphisms in the category, and this is called the partial defect network. The reason for partial will become clear in a minute, and actually this works in the first place. There are no physical boundaries, but if there are, then there is a prescription of replacing the worldsheet by something called a complemented worldsheet, defined as follows. Remember, physical boundaries or boundary conditions are labeled by objects in the category of A modules. If A is the phase, let's call it small a here, but the category A modules can be they of right modules, but single orientations suitably. This can be thought of as one A bimodules. And now one simply says that in such a situation, I add an additional 2 cell to my worksheet, which I label by 1. And then there are some technicalities that you have to take into account. But in any case, this way you get worksheets without physical boundaries, but with some extension of the defect network. And then you are back in the situation where there are no physical boundaries. And I will not say more about that. Is actually rather easy to give this prescription in detail, and then one has the result. That the let's call it complementing virtue as tilde, replacing S by S tilde does not result in any changes in the bulk or a defect boundary fields, bulk or defect fields that are associated with geometric boundary circles in on the boundary of the sigma. And that means we do not change in particular correlators of the conformal field theory, but in order to check that, we first have to define the correlators, and this I will not be able to do before the break, but directly afterwards. Before that, why did I call this a partial defect network? Well, here we have forgotten some information, and of course we have to account for the information. By the following prescription, add in each two-patch what is called a full Frobenius graph. And instead of writing a long definition, let me just indicate what that looks like. So if I have a two-patch labeled by Frobenius algebra A, I insert a graph. So this is the path defect network. So the labels are actually bimodules, and in particular from one side they are A modules. And then I just add some graph inside here, such that each edge is labeled by A, each morphism is that there are trivalent vertices. These are labeled by the product and co-product. You can also have equivalents, which are a combination of product, co-product, and co-unit unit. And also each of the segments of the boundary here should be cut. So here I have mu or delta, and here I have representation morphisms. And full means, so any such graph is called a Frobenius graph, and full means that if I add any further edges or vertices, then by using the properties of the Frobenius algebra, so as algebra, co-algebra, Frobenius, and representation properties, I can reduce it to the graph that I had before. So there is a kind of minimal prescription just on each of these segments here. You have a representation morphism, and then you have a number of lines linked by A, and you bring them together by some combination of product and co-product. And it doesn't matter which one. If I have any two full Frobenius graphs, then they are related by Frobenius moves. So I can take any one of them, because in terms of the string nets, then if I interpret this as string nets, then the distinction between two of them will be a null graph. The difference between two of them. Okay. We now are able to associate string nets to worldsheets by first forgetting some information about the worldsheet, interpreting the network of defects that we have as a graph in the sense of string nets, and then adding these full Frobenius graphs. And now if you combine the description of conformal blocks that we had in 724 some time ago, conformal blocks for a rational conformal field theory with based on some modular tensor category C. C is now modular tensor category. then, and this was conformal blocks in the sense of vector spaces with some action of the mapping class group and compatible with sewing. And then the result that I have been describing before, and then you get the following result that for S world shape without visible boundary, but as I just tell you, this is not really a restriction because we can replace a worldsheet with physical boundary by this complemented worldsheet, which does not have a physical boundary any longer. There is an isomorphism between the space of conformal blocks for the worldsheet S and the string net space for the surface corresponding to the worldsheet and a boundary value which is provided by the description that I have given for the graph. And if we take we have on the boundary of the worldsheet, if there are no physical boundaries, we have precisely the information that we need for having a boundary value for this surface sigma. And this is an isomorphism of vector spaces, but not only that, but rather it intertwines the action of the mapping class group. But I don't say anything about sewing at this point. And now we define the string net correlator for worldsheet S with this restriction, which is not important, to be the string net denoted by core Sn for S to be the string net given by gamma S, which is the partial defect network. And the union of that with, let me call this theta, where theta is any two hat, and gamma theta is a full Frobenius graph in that tuple. We look at this graph and then take its class in the string space. And notably, this definition is much simpler than the definition in this TFT construction that I gave. We just take the worldsheet, interpret it as a string net, and that's it, essentially. And of course, there is no guarantee that this makes sense, but then we have to realize that the assignment of such a correlator to a worldsheet is or provides a consistent system of correlators. Remember, there was a family of choices of elements in the conformal block spaces, such that they are invariant under mapping class groups, actions, and compatible with sewing. And you have to show that with this definition, you get that. Now, mapping class group is not so hard because this is described by graphs, and the mapping class group acts in a simple way on graphs. So we simply have to see that these particular graphs are such that if I apply a mapping class, I get the new graph is again the same element Brilliant space, but zooming is a bit more involved. Finally, let's give an example. If you take sigma S to be the torus without insertions in phase A, then we have a representative graph which just contains there is no defect network, so the partial defect network is empty, and then we need just a full Frobenius graph and one way to take that is this one. And remember, this is what in the other description of correlates was the idempotent in the full torus that was obtained by the prescription. But here, this is now the graph is on the surface, whereas previously it was inside the full torus. So we had to go through to 3 dimensions, and now everything is completely two. And then you check that this indeed gives the same result as the other prescription, and if since there should be only in the end one consistent system, you expect that this really gives the same thing, and in all examples you can check. You can do something that is very directly. I wanted to give an application of this to the operator product of defect fields. We have 2 defect fields, which correspond to in such a way it could be that they are actually on the same defect line, and you can bring them close together, and then the tensor product of you have this looks as just one defect field, which you can describe. This is a vertical operator product, but you can also look at the situation that you bring 2 defect lines close to each other with such insertion. Then you have horizontal tensor fusion project, and these you can describe nicely with this approach, but I have no time to do that. But let me mention one important other application. There is an enhanced mapping class group. Yeah. I should maybe, I don't know, I don't remember what notation I have used, but remember when we talk about a mapping class, a relevant mapping class group for a worksheet, and then we require not just that we do a diffeomorphism, but it should leave the defect network invariant up to small deformation. And therefore, this mapping class group is typically much smaller than the mapping class group of the underlying surface. But now it can happen that you have, for example, if you have an invertible defect, then remember we have an equality of of morphisms of this form. Now, if you have these defects as part of your defect network, and therefore then as part of your representative graph for SpringNet, then because of the definition of SpringNet as an equivalence class, both give rise to the same SpringNet. But if you only want to, and the correlator is defined as SpringNet, so for invariance of the correlator, you can allow also for changes like that with defect net. And therefore you have an so this, for example, in a situation where this is somehow embedded like that in a surface, then here you will have additional dangers which are allowed compared to here, and therefore, and then the really relevant subgroup of the mapping class group of the underlying surface is the groups which is obtained by allowing for by looking at the subgroup generated by all subgroups which you get in these different situations. The remaining part, I want to talk about SpringNet constructions for pivotal bicategories. And probably I will not have time to really say much about those, but at least I want to describe some of the bicategorical background of that. And you should think of this really as an appetizer. But the first observation is that when you think of the fact that we work with bicategories, namely the one for cobordism and pro-functors, when we and then with a pseudo functor between these bicategories, then it's not so natural to take as an input datum a category. To take or try to take a bicategory E as an input datum. And actually we need a pivotal bicategory, and I have to say a little bit about that. First, a bit about graphical calculus. Well, we have seen that for bicategories, there is a graphical calculus generalizing the one for strict tensor categories, and again we have to make use of the strictification theorem. And we also have talked about pivotal bicategories, yet, at least in some special cases. Now, pivotal, of course, needs rigid dualities, and these correspond in the graphical description to having one cells. Well, you have junctions of one cells, say F and G, E and F, with corresponding units, eta and a co-unit epsilon. And then we require that the composition of the is the same as this one, with the corresponding other diagram. And in pivotal bicategories, now this works when we have dualities. If we have in addition pivotal categories, pivotal bicategories, and then just like for pivotal categories, we have a graphical calculus on this. And now you have to work harder, and you want to somehow standardize this calculus so that we can make nice use of this. And if you look at this, then you end up in particular with the node corolla. This is a disk. Technically, you take the unit disk in the complex plane, and then you have a graph on it with a single vertex at the origin, and all of these correspond to one morphisms, and the two cells here are there by objects. So F1 is a one morphism from A1 to A2, and so on. And the vertex is not labeled, and that means to this vertex you can associate a vector space consisting of all possible labels, in the sense that when we think again of this as analogously as we did before for with categories, this would now correspond to a morphism in the endomorphisms, in the morphisms from the identity on, say, A1 to the composition of all these one morphisms. But again, starting with A1 is a choice, so you can split up at any point here. This you call it polarization, and you have to make sure that things are independent of that. Anyhow, for some choice, and then you describe the actual space as a limit, you get called this a corolla. You associate with this vector space H of the corolla, which really is a limit of. Now you take morphisms in the home category from of, say, any I itself, and then the identity on AI, and then Fi, maybe Fi plus one. I haven't been haven't checked that you know, plus one and so on. And so here we associate with this vector space, but actually you can show that you can extend this assignment to symmetric monoidal functor. From a category of from the cylinder. From a category of corollas labeled by the bicategory B to vector spaces, and I call this GC, that is the mind of graphical calculus for B. Where here the objects are corollas, and the morphisms I need some time to explain. And instead of trying to give a complete definition, which needs a lot of time, I give you an example. Assume you start with you want to have a morphism from two corollas which look like this. And there are orientations which I suppress, such that we have F1, F2, F6 here, and the labels of the two cells are A, C, and B, whereas here we have F6, F5, again F5, and F4, where in order that this makes sense, you have to have two different orientations here, but I will suppress them. And then the labels are B, C, A, and B. And you want to have a morphism of this to a corolla which looks like this. F1, F2, F3, again F3 and F4. And A, B, C, B, A. Then what you do is you take this codomain corolla and remove some part in the middle. You cut it out. Let me see whether I can get this. I have F1 here, F2 here, F3 here, another F3 here, and F4 here. That's it. And then I put in a network such that at these places we have the domain corolla, so I could connect these like this. And here I have F5 and F5, and no F5 outside, so I combine them like that. And here I have F4. Here I have F3 and F3. They do not appear here. So also these I have to connect like that. And this would be a morphism from these corollas to this corolla. In the case where the codomain corolla is from this disjoint union of corolla to one. If in the codomain we have a disjoint union of corollas, we take the disjoint union of some things. And composition is if you have one of them if you have two of them in the second one, you cut out again something in the middle and you glue in the first one. And you may imagine that writing this up in ordinary language is not so easy. Also, there is a symmetric monoidal structure on this category that we can talk about, the symmetric monoidal functor, which is just given by this joint union. So this is the category. Now, what about the functor? An object. This is easy. I have a disjoint union of finitely many corollas. Each of them I have associated a vector space H already, and I just gave the tensor product of those. And on morphisms, again rather lengthy. Roughly, what you do is you choose elements in these vector spaces for the domain that you get in the domain and look what this is mapped to by yeah, it's hard to describe. Maybe I save time. I'm not going into detail, but in any case, there is a result which says that PCB captures the graphical calculus on this for hyperbola. Also important for some aspects is that when you want to work with these morphisms, there are many different possibilities. Even describing them, the general possibility is very lengthy, but it turns out that you can restrict to special types, namely any non-trivial morphism in this corolla category is obtained as a finite disjoint union of partial compositions of four types of special morphisms, and partial composition means that you do composition in the way that I described, but maybe not for all of the corollas involved. And then there is one type which looks like this, so all of these go from two corollas to one. And the original corollas are here, and I can anything any further lines here. The second one is that I just have singled a corolla to start with. Like that. And I close these like I did here in one case. And then the third one is of the following that I against this a situation like that where there can be more things here. And then finally situation where I have again just one corolla to start with, and this is treated in the same way as here, and then there is one additional line like that. And the first two ones I will call connected, and the other one is disconnected. If I ever come to the point where I yeah. Then possible using a little bit of extra time. We need actually some further bi-categorical input independent of this graphical calculus. And if I now say functor between bi-categories B and B prime, I will not use this in the way I did last time, where I identified this with pseudo-functor, but this need not be a pseudo-functor. It just require the data of a pseudo-functor, but not all of the the functorial data, but not all of the natural transformation data. So in particular, I can say that I have a Lux functor if there are natural families of natural transformations F2 and the natural transformation F0, which account for compatibility with the composition in the home categories and with the identities in the home categories in one direction, and co-Lux, and then obviously in the other direction, and the pseudo-functor, which I just called functor previously, is that these are mutually inverse. So in particular, they are isomorphisms. But there is another way to combine them, and this is called an Frobenius functor, which is a two-category version of the Frobenius identities. I would need some time to draw this or write it out, and then there is also a notion of rigidity for such a functor, and then there is a proposition which says that to any rigid Frobenius functor, there is associated a canonical monoidal natural transformation of the following form. I take almost the corollas for the bi-category B. I use this functor here to get the vector spaces. I consider the corresponding corolla categories for B prime. And then associated with this F, there is a functor here, which is called F star, and a natural transformation, which makes the diagram commute. I have, yeah. And this is not actually true, but it is true if I restrict to, I would like to connect it. Disconnected. Where I mean that I only look at the non-full subcategory of corollas, where I take all objects, but among the morphisms, only those which come from such connected types of morphisms. The reason why one has this incomplete result will become clear in a few minutes, hopefully, because we will look at functors which are of this type. But also if f is indeed a pseudo functor, I should not have written this here. By the way, a pseudo functor implies Frobenius functor, which is not hard to see once I have given you the definition, which I didn't, and then you have this analogous statement here without a connector. So if you have a pseudo functor with bicategories, then these graphical calculus functors are related in a simple way. And now I come, that's all I really want to say about this aspect. And now I specialize to a situation which took of interest in connection with what we did before, namely there are two strictly pivotal bicategories. That arise naturally in our context. And actually, one of them we have already seen, the other one almost. The first, if the D-looping of pivotal tensor category. We have seen that this is a bicategory, and you can easily check that in the general case of a monoidal category, and if I have pivotal structure here, it uses a pivotal structure on the D-looping. And the second is we looked at this in 6.111. There we also looked at an example where you look at bicategorical algebras. If the algebras are actually Frobenius algebras, then I call it FR of C, the objects are Frobenius algebras. One cells are prime modules, and two cells are prime module morphisms. And there is actually, I might have forgotten here. There's also a notion of separable, which is again the same as I introduced for ordinary Frobenius algebras, which was this picture here. And there is rigid Frobenius functor between these two categories, which I denote by U. Which does what? Well, first on objects, I have Frobenius algebra A. I don't have much choice because BC has only a single object, so I have to map to that. If I take a bimodule X, I map it to the underlying object in C. And if I have a bimodule morphism, I map it to the underlying morphism in C. And you can actually give the structure of Lux and Oplux functor, which then fit together to a Frobenius functor explicitly, but I will not do that. And now I have officially 5 minutes, if I will extend to a bit more than 10. But I use now this to define bicategorical version of string nests. whereby category refers to the input data. See how much I want to say. Well, the motivation is, as I already said, we have a situation when we look at worldsheets where we have labeling by of 0, 1, and 2 cells, but an ordinal description when we use the category C as input datum for the stringnet, and the definition of stringnet correlators that I gave only uses labelings of 0 and 1 cells, and then you had this addition you had to make for neglecting some of the information by inserting these full Frobenius graphs. And now instead we say we take this directly by using two graphs. These are graphs where we not only label the vertices and the edges, but also the two cells. And we label the two cells by elements of the two category. And then the morphisms, the edges by one cells, and the vertices by two cells. And then let me just give the final result first. For B pointed strictly pivotal bicategory, there is a modular functor analogous to the one that we had for categories, and we call it again S and D, which goes a valid of the same form. But we have these the bicategories as input, and it has nice properties. And this is then a symmetric monoidal pseudo functor between these bicategories. Just to tell you some aspects of the construction. They are not abstractly complicated. There are some complication of technical form, but we define first the boundary value, say on a circle. Previously, we had labels on 0 cells. Now we have labels which are one morphisms, F1, F2, and so on those. But on the 1 cells between, we have the corresponding objects. Then we can define the ascent of all B-colored 2 graphs that have a corresponding boundary value. And we can look at the vector space generated by them. And we can define the null graphs in the same way as before in the null space. And then we can define the stringnet space S and B0 of sigma B to be the corresponding quotient as before. And Then the next set were cylinder categories. Where objects are boundary data, and then morphisms are now string nets in the new sense, group graphs, which are compatible with the boundary values. Not much new. And then you show that this way you can extend this to actually in the same way as before. And then you also see again that the categories that are not either complete and complete, but you need to complete them. And then one can show various results, which in the end give you this main result that I started with, and in particular you get again an expression of the Greenland spaces as in the situation where you look at gluing of surfaces in terms of coends, and then you have our modular function, which sends one manifold to the cylinder category and a two manifold to the item total completed string net space. And let me just give you finally three two results in the remark or something like that. What you can show is that if you take as your bi-category the delooping of a pivotal tensor category, then we just get back the same spaces as before. Same, of course, here you have a boundary datum of this type, but you get a boundary datum of the categorical type by just ignoring the labels here, which means on the string net from a two graph you get an ordinary graph. And the second result is that when you look at the particular case of the interval, then remember previously in the previous situation where we start with a category, this is canonically isomorphic to the category itself. In this case, it's canonically isomorphic, monoidally canonically isomorphic to the endomorphism category of the this would be, I forgot, we didn't complain. And now it's no longer there. I forgot to say this. In the statement, I said that we need our bi-category to be strictly pivotal. I didn't say before strictly, but we can strictify it, and we have. But then I also said pointed. And this requires that there is distinguished object. In the case of, and this I thought the star, and this is what appears here. And in the case of BC, there is only one object, so this is the distinguished one. In the case of Frobenius algebras, here there's a distinguished Frobenius algebra in the tensor unit. And then in order that this that you get this, so maybe one could not here at B. This should come as a distinguished object, which has some natural. And then finally, if F EB prime is a rigid pseudofunctor, between pivotal bicategories, then there are canonical mapping class group option intertwiners between the corresponding stringnet spaces already before idempotent completion. And also the collection of all of these is compatible with zoning. So that means for the result of the construction, the bicategory B is relevant only up to rigid pseudofunctors. So we get just the same results. Now, finally, if you try to apply this to this situation, U is not a pseudofunctor, it's only a Frobenius functor. So it's not true that for these two categories, I will get the same stringnet spaces. And that we know, by the way, we would expect, because we have seen in the case, in the description of these correlators, we had to add this full Frobenius graph. And the full Frobenius graphs just compensate for the lack of U being a pseudofunctor. And that's it for today and for this lecture. Thank you.